Great pleasure to introduce the first invited talk of CPP. We have Andrew Appel from Princeton University, where he's the Eugene Higgins Professor of Computer Science. Andrew is well known by this community, so I probably don't need to do much of an introduction, but he's the recipient of many awards, including an ACM Fellow, and for many contributions to both service and research. You might know him as the author of many textbooks, including the classic Compiling with Continuations, Modern Compiler Implementations, and more recently on Verifiable C and Verified Functional Algorithms. So he's an expert on compilers, verification, programming languages, and he's particularly well known for his work, among many other things, on Standard ML of New Jersey, various projects related to computer security, authorization logics, voting machines, and the hacking thereof. And more recently, he's been working on verified software toolchain. And so he's a real expert in sort of formal verification of the kind that we see here. And so with that, I would like to welcome Andrew to the stage, and I'll switch over to his presentation. For those of you here, let's give him a round of applause.
Now, did I unmute? Can someone tell me if I unmuted successfully?
Yes, we can hear you.
Okay. Great. All right. I'm glad to be here, and thank you for the invitation to talk about what I'm interested in these days. And what I'm interested in these days is sort of verification engineering at sort of top to bottom at scale. I read this interesting survey paper recently about sort of how verification works in proof assistance at various levels. And they explain you can't really publish this, really, these design principles. You can't find them in standard places. You have to find them in places like invited talks. So here I am. Let's prove programs correct. As you know, to prove a program correct, you need a specification. So you have a program, you have a specification. In what language should you write your program? In what logic should you write your specification? Somehow this connection between the logic of what you write your specification in and the language that you write your program in is a program logic. That's what I mean by program logic. You might want your program logic to be sound. That means it has to be sound with respect to something, so you need a semantics for your language. And because programs and programming languages and semantics and all this stuff are sort of large and a moving target as people commit more things to GitHub, you really want this all to be mechanized. So these are just the basic requirements for doing program verification. You might want to compile your program, so you might want a compiler. When you prove your program correct, you want to prove it correct with respect to the high-level spec for what it was supposed to accomplish for you, not how it accomplishes it. But it's often useful to modularize your proof of correctness with a low-level spec that really is about how it accomplishes it, and you layer your proof. You prove your program correctly refines the low-level spec, and you prove that the low-level spec gives you the high-level properties you want. So now we need a correctness proof for the compiler if you're ambitious, which means the machine language also needs a semantics. You could go down even further because machines get implemented, and people do that, and that's a good thing, but I just couldn't fit it on the slide here. But what's the proof? What's that in between the low-level spec and the high-level spec? That's not exactly a program logic, is it? What is it? And is the high-level spec written in the same logic as the low-level spec or a different logic? What's going on there? And that's one of the things I really want to focus on, especially in the second half of this talk, is how you connect at the higher level. regardless of all of that, you want to avoid errors when you try and connect the layers together. If you prove that the low-level spec correctly implies the high-level spec in a different logic and proof assistant from the one where you prove that the program refines the low-level spec, which is in a different logic and system from the one where you prove that the compiler is correct, then there may be gaps, misunderstandings of what the specification interfaces mean. So it would really be a good idea to be able to seamlessly connect all these proofs in the same logic. So let me talk some more about low-level specs. You could call this an algorithm. And the difference between an algorithm and a program, you well understand. An algorithm is concise and elegant and written in the textbook and analyzed, and the program has a lot more details to it about how everything gets represented. We could also call it a functional model. The functional model might even indeed be a function in some specification language like Galena, which is Cox's functional programming language, or ML, which is Hall's functional programming language, or something like that. It doesn't have to actually be a function. It could be written as a set of inductive inference rules. It could be written as a relation. And then finally, in what language should we write the program? The angels might disagree. Clearly, you should write your program in a pure functional language with an expressive proof theory so that you can reason about your program effectively. Or you could just write it in C. Usually, you should write your program in a pure functional language with a clean proof theory, but sometimes there are reasons for writing it in C having to do with interfacing to low-level models, latency, and sort of access to algorithmic issues that you want to control the hardware in a certain way. The C program might be the runtime system of your beautiful functional language. So if you were going to write your program in a functional language with an expressive proof theory, you could, write it in the language of your logic if you use a logic that has some sort of lambda calculus embedded in it. And then your general purpose logic of your proof assistant is the program logic for your functional model, and that is a good thing. And you can do this in a variety of modern proof assistants. A modern proof assistant is one that was invented in the 20th century, as you can tell. But there's a point to that, right? The word ecosystem is in the title of my talk. It's those proof assistants that were invented in the 20th century and have lasted that have developed the kind of ecosystem that will become useful in a way I'll describe. Okay, so let's talk about how you connect the program to the low-level spec. Well, if you're writing in a programming language that's a pure functional language in your proof assistant, then the program is a functional program and the low-level spec is a functional program. Maybe they're the same program. Can we collapse these two levels? Sometimes, but not always. Here's the Fibonacci function. This is the mathematical specification of Fibonacci written down maybe a little bit clumsily in Coq, but fib of n is defined in terms of fib of n minus 1 and fib of n minus 2. If you ran that program, you'd notice that it takes exponential time. You want the kind of iterative Fibonacci that we might think of as dynamic programming that keeps track of the last couple of values. So there you can write that as a pure functional program in Coq that looks a little more iterative and imperative. And then you can prove that these are equal or equivalent. Well, equal if you believe in extensionality. So here's a theorem that the low-level functional, the program, the one in blue, correctly implements the functional spec, the one in peach. And so even if your functional language is the one that you're writing both the spec and the program, they're not necessarily the same thing. So can we write pure functional programs of any interest and effectiveness and prove them correct? Well, Concert is a pure functional program in Coq. Proved correct. Does useful things. CakeML is a pure functional program in ML, proved correct in Hall 4. Also does very interesting things. Certicoq is an optimizing compiler for Coq, proved correct in Coq. So definitely we can write pure functional programs at scale and prove them correct. Although you notice these are all compilers. There's something special about compilers. They think deep thoughts but don't interact much. And so sometimes for programs that think thoughts that may or may not be deep but interact in a certain kind of low-level way, you may want to program them in a lower level, maybe even imperative language, if you don't want to worry about the sort of latency issues of garbage collection and so on. So suppose we program in C. We certainly don't want to write our low-level spec in C. We want to write our low-level spec as an algorithm, a functional program in Coq, or an inductive relation, or a set of inference rules, or relate, whatever. So we'll need the program logic, the C compiler. And this approach is what we did in building the verified software toolchain. So what is the verified software toolchain? It's a foundationally sound, higher-order, impredicative, ghostly concurrent separation logic in Coq with tactical proof automation for a real programming language. There's another interesting system out there, Iris. Very cool. It's a foundationally sound, higher-order, impredicative, ghostly concurrent separation logic in Coq with tactical proof automation for some real programming languages. Iris is more a framework for building those things than VST is a thing. And Iris has some interesting advantages. Its internal impredicative logic is built with a more modular construction than the rather similar construction in VST. In other words, the way that separation logic is intertwined with the impredicative modal logic in VST has been teased apart in a more elegant way in the construction of Iris. On the other hand, the application of Iris to some real programming languages like Rust and C and C++ and others is, at this point, a less well-developed thing, as far as I can tell, not for the theoretical ideas, which are very cool in those papers, but for the sort of practical, usable thing at scale. But it'll come. Right, and it's foundationally sound, provided that you actually do the proofs to connect it to the operational semantics of your programming language and compiler. And that also is, seems to be coming along in the Iris community. So let's prove C programs correct. Let's say using the verified software toolchain. So C programs, that's an imperative programming language. We need either Hoare logic or abstract interpretation to reason about that language. Let's choose Hoare logic. Let's prove them correct, not just safe. So we need to reason about their specification in the mathematics of the application domain. And that means the assertion language must be an expressive general-purpose logic in which you can reason about many different application domains. So let's choose Coq. The C programs use pointer data structures. So that means our Hoare logic should be separation logic, which is designed to reason about the sort of anti-aliasing assertions you need to maintain when dealing with non-trivial pointer data structures. The C programs we want to be modular. We want modular C programs, and we want modular verification of modular programs. And that means we need abstraction in the program logic to deal with abstraction in the program, so we need some sort of higher order logic in which we can quantify over predicates. And the modularity may be all sorts of complicated object-oriented patterns, for which it turns out we need the program logic to be impredicative, which means that if I quantify over stuff, then the stuff I quantify over could also be things built with quantifiers in a way that I won't need to, if it were a predicative system, I could still do that, but I would have to sort of stratify the levels and quantify over only predicates at a smaller level. And that turns out not to be good enough for the kinds of object-oriented patterns that occur in programming. Oh, and of course, C programs are concurrent, so we need a concurrent separation logic. So that's what we need. We need to prove concurrent modular object-oriented C programs that use pointers correct. So we should use a higher order impredicative concurrent separation logic embedded in Coq. It just follows from the demands of what we needed. But of course, you might worry that a program logic like that would be hard to use and also hard to trust. You put all these features in your logic, and now it's not a very small logic. Why would you believe that it's sound? So we should prove it's sound in Coq with a machine check proof with respect to the operational semantics of the programming language of C. But the operational semantics of C is far too complex to trust as a definition. So let's prove it's sound with respect to the CompCert C-Lite operational semantics with respect to which CompCert is proved correct. And then, even if that weren't actually the operational semantics of C, at least we have an end-to-end proof about the behavior of the machine language program. But actually, CompCert's operational semantics is designed to really be faithful as much as possible to what GCC and Clang and the C11 standard are actually doing. Those three things don't all completely agree with each other, but to a large extent, the semantics is designed to be what we understand to be C. And that will mean that in this tool chain, if you prove your C program correct and run it with, and compile it with Clang or GCC, you still get a pretty good proof about your source program that is useful, although it doesn't have the foundational guarantee you get by using a proved correct compiler. So we'll use a foundationally sound higher order impredicative concurrent separation logic embedded in Coq. But a logic like that would be practically impossible for any ordinary user to use in proving their program correct. So let's build a proof automation system using Coq's lemma and tactic language to help users apply the program logic to their programs. And that's the verified software toolchain, in the middle of which is this expressive program logic called verifiable C, which is basically a HOR logic, so it has preconditions and postconditions. And the rule for the if statement in this logic looks like the rule for the if statement in any kind of HOR logic. So here's a program we want to prove correct, maybe imperative list reverse. You'll recognize this program maybe from the very first page of John Reynolds' very first paper about separation logic. And this program walks through a list, reversing the pointers, but leaving the con cells in place. So you end up with a destructive in-place reversal of the list. So to prove this program correct, we'll need separation logic because it deals with pointer data structures. And the purpose of separation logic is to encapsulate in a nice logic all of the anti-aliasing conditions about this pointer does not point the same place as that pointer. And so it has precondition. If the state satisfies the precondition, then it's safe to run the command. And the state after running the command will satisfy the postcondition. And we write all of these assertions using separation logic. That means each one has a footprint. I won't go into all the details because this is quite familiar to most of the audience by now. And so here's a picture of a list on the left and a description of that list. And an assertion is matched by a heaplet, which is a partial function from addresses to values or addresses to records. And the separating conjunction is the disjoint union of these partial footprints. And we use quantifiers in separation logic to abstract over the internal pointers. So the top assertion and the bottom assertion both describe maybe the same list. But the top one says, oh, and the second cell of the list is at address Y. And the bottom assertion says, well, there exists an address Y at which the second cell is to be found. And that allows you to abstract, the beginnings of a linked list with a certain head pointer, but you don't care where it goes from there. And so we can make a sort of fixed point definition of linked lists in separation logic. This is also not new. It goes back 20 years now or more. And we can describe it in Coq in VST's separation logic. And this thing in blue is just a user definition for a particular kind of linked list. Separation logic allows you to build these kinds of data structures. So now we have one of the tools we need to specify and prove this program. Let's run the program. We start with P pointing at the beginning of the list. We initialize a couple of pointers, and then in each iteration of the loop, we find that W is pointing to a list pointing backwards from the middle, and V is pointing to the rest of the list still pointing forwards. And as we do more iterations, we have reversed the whole list. And that's a proof, really. I mean, in 1979, that would have sufficed as a proof of correctness of this program. But now we want a formal proof. But these pictures have given a hint about what the loop invariant should look like. First, we need to specify the program. So here's a specification in yellow. If before running the function, P is a linked list representing sigma. So P is an address in memory of the C program. Sigma is a sequence, mathematical sequence. Of course, in Coq, we describe mathematical sequences by the inductive data type of list. So sigma is a mathematical list that is represented by the data structure rooted at P. And after running the function, the return value of the function is the address of a linked list representing the reverse of that sequence. This program has a while loop in it. The while loop rule in separation logic just looks like the conventional while loop rule for Hoare logic. And it needs a loop invariant. So here's our loop invariant. At any point in the middle of the execution, there exists a subsequence sigma 1 and a subsequence sigma 2, so that the original sequence sigma is the reverse of sigma 1 concatenated with sigma 2. And W is a data structure, is the address of a data structure that represents sigma 1, and V is the root of a data structure that represents sigma 2. And so we can, the thing in yellow is my sort of informal description, really, of the specification of the function, but we can write it all down in Coq in VST's notation for that kind of stuff. And it's got a precondition and a postcondition, and I just point out that this with clause binds variables that can be seen by both the precondition and the postcondition. So they can talk about how what's in the postcondition represents something related to what was in the precondition. And similarly, we can write down the loop invariant in the notation of VST in ASCII, so to speak. And then we just write a proof script. So here's the beginning of the proof script. This forward just says, do one more step of forward symbolic execution, where the symbolic states are just assertions in the separation logic. So you can go forward completely automatically through ordinary statements, but when you get to a while loop, you need to supply a loop invariant, because VST is not going to figure that out for itself. So there's the beginning of the proof script for the first 3 statements of the program. As soon as you've done a forward while, you find that you have to prove that the precondition implies the loop invariant. You know, your current assertion before the while implies the loop invariant. That the loop invariant implies that evaluating the loop test will not crash, right? The loop test accesses memory and does comparisons and does maybe additions and multiplications, and those might overflow. So your precondition has to be strong enough to prove that nothing will go wrong in the execution of the loop test. Then you prove that the loop body preserves the invariant. And then after the loop, the invariant is satisfied and not the loop test in the usual way for while loops, and you have to prove the rest of the function body after the loop. And then here's, you know, the rest of the proof. So it's longish and verbose. Each ordinary step of forward symbolic execution is just one word. It could be less than one word. It could be log n words, or even constant number of words if you want to use the repeat command in Coq. But occasionally you have to sort of refactor your assertions to expose things that had previously been abstract. Okay. So we can use that to prove that the C program implements its functional model. But where was the functional model in all this? Well, there it is, rev. The functional model of what this in-place list reverse does is the mathematical reversal of a sequence. It's very easy to say math, but actually we have to write down that math in the logic, and of course that's written down in Coq's standard library. But there it is. This rev function is the functional model for what we're doing. And now we can reason about the properties of the functional model. And it's convenient that actually in the Coq library are all these kinds of lemmas and theorems about the properties of rev. So much of that is done already for us in this case. So, you know, the program logic has preconditions, commands, postconditions. It has a context that gives the types of the local variables and the specifications of the global functions, all of these sort of less local and more global things you'll need in order to do these proofs. It has a notion of entailment in context, and these entailments are the kinds of things you would use to prove the rule of consequence in your core logic. And it has a rich set of operators, as you might expect. Okay, so here's a couple levels already of how to build the proof that your machine language program implements the very high-level thing you wanted. And I illustrate here with CompCert, but you might be able to do something else down there. I illustrate here with the verified software toolchain, but you know, you have alternatives there, all that fit in this general framework of layered verification. You could use some of these other proof systems for C programs or imperative programs, Daphne or Verifast or Framacy. But the problem there is that their specification logics are not general purpose expressive higher order logics in which you can do abstraction well. You know, you'd have to port specifications over between them and Hall or Coq or whatever. And they're not proved sound foundationally with respect to the operational semantics of some language. Anything they know about the programming language is mixed into their implementation in ways that it's difficult to tease apart and trust. So what else? You could use Coq. If you were programming in Coq and you wanted a proved correct compiler for Coq, I would recommend Certicoq to you. If you're programming in sort of the functional ML inside of Hall or Isabelle Hall or whatever, you could use this proved correct compiler. In fact, this proved correct compiler comes with its program logic, a characteristic formula for ML, in which you can actually prove things about imperative ML programs as well. So this layered approach has many different varieties, and they can all be sound and interesting. But what's up there? How do you prove that your functional model correctly implements the high-level spec. So let me give some examples. My students Zoe Paraskevopoulos and John Lee had a paper in ICFP last year in which the entire optimizing back end, the sort of anormal form optimizations of the Certicock compiler are proved correct. So you can think of it as compiling with continuations, but all proved correct in Coq. Last year, Yves Berthaud and I published a little paper about doing floating point proofs, Newton's method, to prove that this C program that is doing floating point to by Newton's method to compute square root actually accurately and correctly computes the square root of n. My student Josh Cohen did a proof last year about forward erasure correction, a non-trivial C program that had been in use for 25 years doing a kind of Reed-Solomon coding by a Gaussian elimination presentation of algebra over finite fields modulo primitive polynomials, all of which you could prove that it actually reconstructs the missing data. A few years ago, we proved that HMAC DRBG, which is a standard, very widely used cryptographically strong random number generator, is actually cryptographically strong and doesn't have any backdoors in it. And related that then to the C program in OpenSSL or Embed TLS. And we did something similar for HMAC cryptographic authentication, proving about the inability of the attacker to find a collision, which you don't want the attacker to be able to authenticate something that you didn't authenticate. And you can do an HTTP server that way, as was presented in both CPP and IPP in recent years. Okay, so, and recently we proved Xingyi Wang and others proved a generational garbage collector correct. This is the garbage collector for Certicock, but it's written in C and it proved correct in VST. But you need to reason about graphs. And separation doesn't naturally reason about graphs where two different things can point at the same thing. That's aliasing. So to reason about graphs, you can do it in separation logic, but you need a theory. So underneath all of these, well, if it's a functional program, as this was, your program logic could be Coq. The rest of these were C programs, so the program logic was VST. But what's the logic used to do the proofs up here? And the answer is various. For proving compiler optimizations, we have a kind of construction of step index logical relations. For proving Newton's method, we have the construction of floating point in Coq and reasoning about interval arithmetic over Taylor series. For the error correction, where we have finite field matrix multiply, we use the mathematical components library, which is good at reasoning about linear algebra and mathematical abstraction. For the crypto proofs, we use the foundational cryptography framework, whose application domain is the computational monad of probability spaces. What are the probabilities? The probability that the attacker will be able to guess the next bit. For the HTTP server, the application domain is sort of interactions, for which we use interaction trees. That's another library in Coq. And for the garbage collector, when we want to reason about graphs, we use the Certigraph library. And I participated in most of these proofs, but none of the libraries in purple are mine. I got to use other people's libraries. And here are the other people. I can only do these proofs by leveraging what the community is building, and only if the community is not dysfunctional. And so what I want to tell you about is how encouraged I am by the ability of the community to have all these packages that work, and why that might be. So the foundational cryptography pack, and I'll just give you a little tiny catalog of useful libraries and packages. There's many others out there. But when you want to prove programs correct that do things in different domains, you need the mathematical tools to reason in those different domains, and you have to look around for where to find them. So the foundational cryptography framework, built by Adam Petcher in his PhD thesis at Harvard, is based on a theory of computational monads over probability spaces. And so we used it, for example, to prove that the attacker who can do only 2 to the k steps of computation can, let's say 2 to the 100 steps of computation, can guess the next bit of your random number generator with probability no better than 0.5 plus, I don't know, 2 to the minus 70, right? The real number library, we don't usually compute in the reals because, you know, in my lifetime we've gone from 16-bit machines to 32-bit machines to 64-bit machines, but we're not going to get to machines whose word length is wide enough to represent the reals anytime soon. But the real numbers are really useful for reasoning about programs that use integers and floating point. For example, the real numbers satisfy the associative law. Floating point does not. So when you start reasoning about numerical programs, even the integer, the signed integers in C don't satisfy the associative law because of overflow. So when you reason about programs that use numbers, you very often want to lift your reasoning to the reals as soon as possible and reason that way. Flock is a formalization in Coq of the IEEE 754 floating point standard, which is a very well-designed standard. Its designer won the Turing Award very much for that, in addition to other good work he did. And it turns out that you can represent this standard in logic reasonably well. It was first done by John Harrison in Hall Light about more than 20 years ago, maybe 25 years ago. It was done in Coq a dozen years ago. And this is our basis for reasoning about algorithms that use floating point. And then on top of Flock, its authors built a package for interval arithmetic. So interval arithmetic is, you know, if you can bound the error in a certain number between a low value and a high value, and you can bound the error in some other number between another low value and high value, and you add those together, then you can bound the error between the sum of the lows and the sum of the highs. Now, if that's all you do, that's very naive, and things blow up very quickly. You know, if your interval is between minus 0.1 and plus 0.3, and you divide by that number, then you've already blown up. So the interval package takes Taylor expansions of the symbolic things you want to say and reasons at higher order in ways that are much less likely to blow up. Right? It is not just a kind of dynamic keep track of the lower and upper bound. And it's in Coq, right? Generates proofs in Coq. GAPA is a package for expressing what floating point operations do in terms of those intervals so that you can explain what floating point programs are doing by means of the error bounds on what they're computing. GAP is actually written in C++. It was originally for the PBS system, but it generates proof witnesses that Coq can check. VC float is a kind of competitor to GAPA, if you like. It operates in roughly the same domain of reasoning about floating point and reducing your representations, specifications in floats to things you can reason about using the interval package. And we've been using it recently. It's sort of more tractable to use VC float instead of GAPA because we want to use its individual components and repurpose the components and improve the components to do our tasks, which is easier to do if it's all in Coq and we can get at the components more easily than a sort of monolithic C++ package that generates witnesses. VC float was built for the Defense Advanced Research Projects Agency 8 years ago, plus or minus 6 years ago. Published in CPP, a great conference, and then not maintained since. And it was published by a profit-making private company. But 10 years ago, DARPA said, well, you should really open source all the research you do for us. So there it was on GitHub in an open source repo. And it only took a couple of weeks to port it to, the modern version of Coq and the modern version of CompCert and the modern version of Flock. So even something as out of the field as DARPA's decision a decade ago that they would like the research you do for them to be open source contributes to the health of this ecosystem. There is, of course, the mathematical components library, which was, the beginnings of which were built a long time ago to help prove the odd order theorem, but is now sort of generally useful for all sorts of kinds of algebra and abstract mathematics, rings, fields, matrices, and so on. Certigraph is the theory of sort of directed graph data structures embedded in separation logic. And it's described in, I guess, this OOPSLA paper that I cite. And now think about, a generational garbage collection. Actually, Certigraph has been used for things like proofs of imperative programs that do union find and Dijkstra's algorithm and Prim's algorithm, in addition to garbage collectors, which you can think of as a kind of breadth-first search. But generational collectors are breadth-first search that have to keep track of several different regions and the interpointer relationship between the regions. And it's nice and expressive for that kind of thing. And then when you want to reason about the semantics of your machine language program, you want to use the semantics of an actual machine, not a toy hypothetical machine that's only good for publishing POPL papers about. So in defense of POPL, this paper appeared at POPL. It's from Peter Sewell's group at the University of Cambridge, and it's a system for describing machine instruction sets in ways that you can produce their formal descriptions in Coq or Isabelle Hall or whatever, and comes with some actual machine descriptions of real machines that you could actually trust. Here's another useful library. I haven't used it much yet, but this is sort of the IRIS group's extended standard library of functional models of data structures, for example, such as lists, trees, lookup tables, tries, monad notations, equality simplifier, et cetera, et cetera. OK, so here are the layers. At the bottom, maybe you want a verified compiler. In the middle, you want a program logic for your maybe imperative programming language. And at the top, depending on your application domain, you'll want some combination of these libraries and tools. You can't build it all yourself. So you should use all those libraries maintained by these different groups and hope for the best. Yeah. And then you will be in DLL hell. And let me explain to you DLL hell and what is the clock platform to help you get out of DLL hell. So this is DLL hell. The name comes from the 1990s, the dynamically linked libraries of Windows. And it can be more generally called dependency hell. If you want a 21st century term for it, you could call it dependency hell. Let's say we start with Coq. And on that, we have the CompCert specification of the operational semantics of C. And on top of that, we have the verified software toolchain, its program logic and tool set for proving programs correct. And for the part of the operational semantics of C that deals with C's floating point, for example, we use the flock library. That is, CompCert uses the flock library, and VST inherits the use of the flock library from CompCert. And now we do a program correctness proof using VST. But the user also wants to reason about floating point in the program at the source level. So uses, let's say, the GAPA library and the interval library, which depend on the flock specification of floating point. But we built VST based on CompCert 3.3, based on, which runs in Coq 8.9, based on flock 2.8. And we have a version of GAPA and interval that are built for Coq 8.11 and require flock 3.4. And it doesn't all fit together. That is dependency hell, especially this pattern of diamond dependencies. And we can't just put another copy of flock in there, 2 copies at different versions, because it's the specification that's relied on the left-hand side of this picture for what the compiler is doing, and on the right-hand side for reasoning about the semantics of the source program. And besides the diamond dependency problem, besides the problem of actual DLL hell, OPAM doesn't even accurately tell you the dependency information. You can't assume that's accurate. So you try and put together your system built from all these libraries and tools, and it won't build. And so here's the solution, the Coq platform, which is a distribution of Coq together with a selection of libraries and plugins that are compatible with each other. And this is a social process as much as it is an engineering process. And so let me explain how it works. Like this. All right, that's the end of the explanation of how it works. And after I submitted the camera-ready version of this paper, I learned more. I learned that Theo Zimmerman had a lot of the important ideas behind this in his PhD thesis. And he's one of the contributors to and maintainers of the Coq platform, and has really studied how you get a collection of open source libraries and tools developed by different groups, but which have to work together. How do you keep that maintained? Notice the word ecosystem even in that paper, right? I have the title, the word ecosystem in my title. In fact, the word vibrant ecosystem is a complete cliche by now, but cliches often are there because they describe something, a useful concept. And here's another interesting paper by Theo about how you keep in sync one of these ecosystems. So let me talk about the collaborative ecosystem and how it differs from when I first started in this field. here was open source in the 1980s. There were a couple of open source licenses out there, BSD and MIT. Those licenses are still in use today. Those two are fairly similar to each other. And we started distributing standard ML of New Jersey open source in about 1987 on magnetic tapes, right? There was no GitHub. There was no internet, really. And so that means we only had one release per year on the average, shipped around to our friends by parcel post with magnetic tapes. And development was all done at the same site, in New Jersey. It's not that we rejected contributions from others, there was just no way to communicate and incorporate them. So that was open source without really the sort of collaborative aspect to it. So in the 1980s, you might expect periodic yearly releases with limited amount of external contributors, limited connection with other tools and libraries, inadequate testing, limited issue reporting abilities. What do we have now? We have continuous open source. Every commit you make of every bug in every branch is visible to the public if you have made your repo public, as you should. You get much more benefit from making your repo public than by hiding the embarrassing bugs that you will inevitably put in your branches. There's easy external collaboration, in part because your repo is public. There's issue reports and ways to keep track of them. There's pull requests, which is a collaboration mechanism. There's conversations in those pull requests. You can look up the conversation from a pull request from 4 years ago to figure out what's going on. There's continuous integration. You make your commit to your pull request, and it tells you whether it built and all the tests work. And there's cross-package continuous integration. The verified software toolchain is one of the continuous integration tests of the Coq system itself. This is what Theo Zimmerman meant by these collaborative package ecosystems. And now there's continuous delivery, which is a buzzword, but what does it mean? It means that if you're pulling the master branch of somebody else's repo, then they have continuous delivery to you. So things work at a much bigger scale now, and it's not because there's more people in my research group. It's because I can collaborate so usefully with so many other research groups that don't even know that they're collaborating with me. So I sent this paper. You can read about this in the paper. There's more details in the paper. Please read the paper. But the program committee said, surely it's not so wonderful as that. Surely there's some pain points in using Coq. So I had to think of a pain point or two. Here's a pain point. We make packages of terms X with proofs about them. So P is some property, a predicate. T, little t, is a package of X of type big T with a proof of its property. So for example, T is some set of Booleans, the true Booleans, to make a trivial example. And A of n is one of these packages that is the package of true with a proof that true is true called big of n. And when I compute A of 10, it's instantaneous, and when I compute A of 23, it takes half a second, and you can see actually computing A of n takes exponential time in n. Now this is a toy example. Here's big of n. It just makes a big proof tree. This is a toy example, but it demonstrates a problem that's very real, that as you compute with these things, the proofs blow up. And when you extract to OCaml, that's fine, because propositions and proofs of propositions drop out of extraction, which is a good thing, and it doesn't bother you. But if you compute inside Coq, things will blow up. And I want to do a lot of computation inside Coq because in my proofs, in my mathematical models of stuff, that I'm connecting at all these levels, sometimes there's proof by reflection. There's computation going on. And you could say, well, don't write that big of N program. Write a better program to develop your proof. But Coq has the principle of proof irrelevance. Which proof I use should be irrelevant. It's bad enough that when I write programs, I have to sometimes disrespect the abstraction layers by caring about how efficient something is down below. But I should not have to do that for proofs. So Coq is sort of broken in this way. And the workarounds are not very good. So I wrote that, and the referee said, great. And then I was told, actually, there's a paper in CPP'22 that shows how to solve this problem for the calculus of inductive constructions. So I failed at finding a permanent pain point. Let's hope that this stuff makes it into Coq. And I congratulate the authors for solving the problem before I even got around to explaining it. OK, so I conclude there is a vibrant ecosystem out there that is useful because we want to prove things in application domains about software. I don't want to do math for math's own sake. You can do that. That's fine. I want to prove software correct. And for that, I need to do math. And I need to do it in all sorts of ways, for which I need all sorts of packages and libraries. And I'm really optimistic that it's all working. Thank you.
Thank you, Andrew. Is this mic working? Great. And for those of you who are online, if you have any questions, you should raise your hand, and the students will connect you to the room. But if there's anyone here in the audience who has a question, now will be a good time to ask. Well, I can, oh, yeah. I'll just run the mic over to you.
Thank you for the awesome talk. As someone from the active universe, I'm very jealous of all the libraries you obviously got. We're obviously a long way behind. I'm interested about the Coq platform that you're developing, that the community is developing. I mean, Haskell has kind of gone the opposite direction, right? It used to have the Haskell platform that came with a consistent set of libraries, and it's now, the Haskell platform is now dying, and it's gone. And now modern Haskell projects are even compiled with either Stack, Manage the Stack, or Cabal, and Cabal manages version dependencies explicitly with bounds. And I'm interested what does the Coq platform know or do that the Haskell community got wrong in order to go in that direction?
OK, I don't know what the Haskell community got wrong, but the Coq platform is a voluntary social process. Coq gets released without its platform, or you can get it with its platform. And library developers can ask to participate in the Coq platform, or sometimes they are asked if they would like to participate in the Coq platform. And what that means is that they are responsible for doing certain integrations of their GitHub tags or GitLab tags with the platform releases. They're responsible for coordinating enough with the tools that they need to be compatible with so that the platform release can come out on time. Right? If people wish, the Coq platform organizers, the people I listed on that slide or in the paper, right, put a lot of work into making the platform happen, which is half dealing with these library developers and half dealing with how should we set up the theory of OPAM and so on to make all this work. So it's a voluntary social process that has to be maintained by a team with effort. But it's not all or nothing, right? You can still use Coq without the platform, and you can still use each of these individual tools from its own place. The platform is just a coordination effort of a certain set of OPAM releases, for example.
Thank you. Before I take another question here locally, are there any from online? Let's see. Are there any differences between an ecosystem for verification and ecosystems in regular software development? How does the Coq platform compare to, I think we just answered that one.
Well, for Haskell, we may have answered it. I think there's a lot of commonality between the issues we face in maintaining a theory of proof developments and the issues you'd maintain in maintaining a collaborative ecosystem of libraries for programming. Proofs are software, and the social issues are similar. The continuous integration tests may tell you a little more, right? If a proof checks, then the proof checks. You don't have to worry maybe quite as large whether your test suite is infinite enough to cover all cases.
All right, we have another local question.
So I was wondering if there's any negative downsides to this. One thing I've noticed as I look through the Coq ecosystem is there's many definitions of the same thing and not always interchangeable. So you either pick xlib or you pick SDVP, but you can't really easily pick both. I'm wondering, and now there's stdlib2 and other projects like that, do you see any issue with the decentralization here?
You know, let 1,000 flowers bloom and then let people coordinate. So I heard quite recently, for example, that 5 years ago you might use mathematical components for your linear algebra and Cocorico for your real analysis. And now people are basically adding real analysis to the mathematical components library, and that may mean Cocorico, fades away. And this is natural, and this is what people need to do as they move forward. So it takes work and maintenance, but it's not hopeless.
All right, thank you. I think we have one more question, time for one more question from online. So Isabel has the archive of formal proofs, which is more or less maintained by developers. It's impressive, but I'm not sure how they manage. If your development is in the archive of formal proofs, then it's maintained. I guess that's more of a comment than a question.
Right. Well, okay, relative to this comment, they may be using a similar mechanism to what the Coq development team itself started to do about 6 or 7 years ago, which is to put several of the major users' packages of Coq into the Coq's own continuous integration test suite. And that way, the Coq team learns up front early in research, in trying out new changes to the Coq system itself, what it's going to break in user programs or user proofs. And, and that helps, I think.
Okay, I think we should wrap up the session there. Thanks again, Andrew, for the wonderful talk. And I guess people are clapping online. We'll adjourn here. We have a break until 10:20 Philadelphia local time. That's about 20 minutes from now for everybody who's online, wherever you are. And with the speakers for the next session, if they're local, I don't remember, I should have looked to see if there are any local, come see us here and we'll help you get set up. Otherwise, show up on AirMeet. Thanks again.